Okay, part two of section 714, solving AC circuits using the power triangle method. We're going to apply it to something that is high voltage related, something that we might explore in electrical power systems. The voltages that are given, these are actual real line voltages that are set in this environment. These transmission voltage, the impedance, the reactance, all this stuff. It's very practical. They're real numbers that we're dealing with. So let's work through this problem and wrap up section 714. Here's the situation. It says we have a single phase 12.47 kilovolt transmission line that's several kilometers long. The line feeds a load C, which is out here, from a substation. The line has a resistance of 2.4 ohms. I don't know why that's 2,4, but that should be 2.4 ohms, and a reactance of 15 ohms. That's a very common combination that you would see when you talk about power systems. There is a reactive component and there's a resistive component associated with transmission lines. The instruments at the substation indicate that the active power and reactive power to the line are 3 megawatts and 2 megavar respectively. And he's asking us to find the line current, the active power, reactive power, line voltage, phase angle between the voltage and the load, and so forth and so on. All right, so lots of stuff to do, but at the same time, we're given lots of information, right? And we can already see some things here, I think, as we sort of start to work through this. How do you even start a problem like this, right? Well, it's a good thing it's worked out for us because all we have to do is work through the example. But anyway, so, here's the substation and, it's at 12.47 kilovolts or 12,470 volts. And at the load, we see a different value here. All right, so there was some loss of voltage, right? And then the active power, 3 megawatts in, 2.8 at the load. The reactive power, 0.75 resulting, but initially it was 2 megavar that we had, and that the current that's associated with this is 289 amps. Okay, and here's some information given to us there that shows the losses of the reactive and active power that are reflected from the substation to the load. All right, so let's work through this, and we'll just take it, step by step in the method that he has worked it out. And I'm not going to show the solution yet. We're just going to stick with this. But the first thing is that we can do, we can determine what the apparent power to the load is. So S is equal to P squared plus Q squared here. All right. And so the what we have supplied is 3 megawatts for active and 2 megawatts for reactive, and that is going to come out to be 3.60 megavolt amps of apparent power. Now, once we know what that is, and we know the voltage associated with it, we can determine what the current is, okay? So I'm sorry, I thought this was given, but this is derived. So if I divide that by the 12,470 volts that we're given, we end up with the 289 amps. Okay, talking power, we talk about big numbers, 289 amps. That's a lot of current, right? The power factor at the substation is active over apparent. And so active is 3 megawatts. Apparent is 3.6 MVA. So the power factor at the station is 0.833 or 83.3%. Okay. In part A, they're asking for the angle between the voltage and the current. So once we know the power factor, we can do that. The power factor is 0.833 cosine angle between the voltage and the current. Okay, so we do inverse cosine of this, and that is going to come out to be, now you guys make sure that you know this stuff. And I know, I know it's something that you had a long time ago, but if you have forgotten how you got to these places, make sure that you go back and be able to punch this in your calculator. So that cosine 1, the angle comes out to be 33.6 degrees, not percent, Dave, degrees. All right, so we've done part of the problem now. We've actually probably done one of the hardest parts of the problem. So what I did here is I'm going to put down what we derived from part A and clean this up a little bit. So there's that information that we got from part A there. All right, yeah, it's supposed to be an 8. All right, now part B says, what is the active power absorbed by the load? Well, what we're given here is this information here for this resistive component of 0.2 megawatts that is dissipated in the line. So the power to the load is going to be P sub L. And then I have an equation for power that says it's I squared R, right? And so the 2.4 is the resistance. The current is 289 squared times 2.4. And that is going to be 0.02 megawatts. And so that's where this value comes from right here, right? So that's where that comes from. Again, here I'm telling you things that are given, but again, this was of course derived from the information that we had. And then, so the active power that's absorbed by the load is, back to the initial is, what's he called? P sub C. Okay, P sub C for the load C. All right, so I had 3 megawatts. And then in the transmission of this, I lost 0.2 megawatts. And that comes out to be 2.8 megawatts that is absorbed by the load. Okay, pretty straightforward calculation there, and all things that we could definitely determine, right? Let's see, while we're here, I think we can do part C. What is the reactive power absorbed by the load? All right, same kind of idea. Q sub L is X sub L times I squared. The current in this one line diagram again is, it's going to be 15 times 289 squared. And that is going to come out to be 1.25 megavar. Okay, at the substation, the reactive power that is absorbed by the load would be the 2 megavar minus the 1.25 megavar. And so what I end up with is 0.75 megavar that is absorbed by the load. Again, this is calculated, once we determined the current and we knew the reactance of that inductor, we were able to make that determination. The next thing we're going to do is determine the apparent power at the load. Very easy. It is the apparent power. Again, I think you're getting the idea here. We use this one a lot. Okay, so the power at the load, 2.8 squared plus 0.75 squared. And that number is going to come out to be 2.90 MVA megavolt amps. And that is the apparent power supplied to the load. The voltage at the load end of the line, think about what we're doing here. E sub C is going to be the apparent power. Now, I'm not going to solve that for us. You know, we've been through that enough. We know that relationship. We're just taking that voltage times current, and we're solving for either voltage or current. We know the current and the total apparent. So the voltage at the end of the line is 10.03 kilovolts. Okay. Now, again, look what we did. We determined that voltage, and we didn't do any, you know, complex circuit analysis. We only used these relationships that we're very familiar with, and we're able to determine what that voltage was across there. The power factor at the load end of the line, it's funny, I look at 151 and he has F sub P, factor of power, but we're talking about power factor is the 2.8 megawatts. Now we know the apparent is 2.90 MVA, and we're going to end up with a very high power factor, 0.965 or 96.5%. The phase angle would be the arc cosine or the inverse cosine of 0.965. That comes out to be 15.2 degrees. And so he says that it follows that the phase angle between the voltage at the substation. So this is load related, right? So it follows that the phase angle between the voltage and the substation, and that at the load has gone from what we initially calculated as 33.6. Now we subtract this 15.2. And so that angle between the station and the load is the difference of those two are 18.4%. And then he says that figure 1718 summarizes the results. And he says we could have found the same values using vector algebra, but because of the simplicity of the power method, so this is very appealing, I should say. So, you know, here's what we came up with. Here's our drawn relationships. Here's all these things that we determined, you know, so here's that initial voltage. Here's our load voltage, substation voltage, load voltage. Notice the situation with the phase angle, right? Between here and here is 33.6, but at the load it's 15.2, okay? And what caused that to change? Well, I mean, we can see these things that cause that angle to decrease. Of course, the current stays the same since it's, you know, we're talking about a one line, one direction situation here of 289 amps. Okay, so I think for probably what we're going to do, we're probably done, I think, with chapter 7. He does go through in the other sections using power and vector notation to work some of these same problems. But we will probably move on beyond, because conceptually there's nothing really that's beneficial for us to go through. We're going to get the same results. The other is just a more complex mathematical relationship, and we will probably go through that. I'll do a quick video on 716 just to point out a few things, and we'll make that the end of this chapter.